So today's video is one in a series of videos that I think cover math topics that are real pertinent to general chemistry too. And the first thing we're going to start with is exponential functions. These include the natural and common logs and the anti-logs, the natural and common anti-logs, 10 to the x and e to the x. And what I'd like to do is just introduce those, kind of help you understand the background behind it, and then really dive into how these are applied in chemistry. And then I want to talk about some skills that you'll find are useful throughout your semester study in general chemistry too. So let's start with the common log, log. And the question is, why would you introduce it? So I'm going to just try and kind of give you a background where it comes into play. And a good explanation can be found when you look at spectrophotometry. You know, light is shown through some sample. The spectrophotometer then measures the amount of light transmitted or the amount of light what we call absorbed. But what we're really going to focus with first is what's transmitted, the percent transmitted. So basically when you see a number, if it said 0.2 on the transmission scale, it's usually reported as percent transmission, which means 20% is transmitted. And that means of the 100% of light at that wavelength, which in this case looks like the yellow wavelength, of the 100% of that light intensity that is passed through a sample, the sample itself absorbs out 80 of it, so 20% of it's transmitted. Okay? And when you hear that it absorbs out 80%, that is the English definition of what we understand absorb to mean, but not the spectrometry definition of absorbance, which I'll explain here in a minute. Just a heads up. But anyway, so here's what you can do with percent transmission. We put in copper at different concentrations. Remind you once again, these brackets assume molarity is what that means. So the copper 2 molarity went from this very small dilute solution, and you tend to increase the concentration. When it's dilute, then most of the light is transmitted. And then as you get more and more concentrated, obviously the light gets less and less, more of it's absorbed by the concentration of copper in the solution. So this all makes sense. I am not reporting it as the decimal. I'm moving the decimal over twice and reporting it as percentage. So if I graph this, then you would see that you basically have an exponential curve. This is not a linear curve. So there is a function that will fit this, and we might learn the chemistry behind how that function fits. But that is really hard to work with. What you like to work with when you do this sort of thing is to get things into a straight line. So here's what we're going to do. We're going to bust out this back to the transmittance, the raw transmittance before it's changed to percent. And we're going to do a little conversion on it. We're going to take the log of it and see how that works. When you take the log of that and then you graph concentration versus log, you get a linear function. So when you have an exponential function and then you graph it as a log of that function, you can usually get it converted to a straight line, and then you're able to use y equals mx plus b, a very familiar equation to us, where you can relate whatever is on the x-axis to the y-axis according to this times the slope of the line plus the y-intercept will equal whatever's on your y-intercept. So you can then translate between whatever you read on the instrument as transmittance back to the concentration of copper that's present. And this all works good, except for it's not really intuitive here because of the fact that you're working down in the negative number zone. So what we've done is one more little math change. What if we were to take, and instead of doing the log of t, let's do the negative log of t, and then we regraph it. And now this is starting to make a little bit better sense, that if you look along this axis, you go, all right, we're increasing concentration, 0.005. We're doubling that up, right? If you double it to here, you get to 0.02, right? You go another 0.01, you get up to 0.03. You're increasing concentration here. As you increase the concentration, this measure of minus log t is linearly increasing. And so it's a nice linear relationship. And this stuff gets the name absorbance. And that literally is what in spectrophotometry absorbance means. So as we know, let's just take a number here of 10, this is easy to work with. If you had 10% transmittance, you would know that 90% of that was absorbed. And that is a different expression than what we call absorbance in spectroscopy, which is literally minus log of transmittance in the decimal form, not turned to percent. And we use that because you then can turn around and say, oh, this is a formula that's familiar, the absorbance, or minus log t, but we call it absorbance commonly, equals the slope times whatever the concentration is plus the y-intercept. And usually this is fairly logical, because if you started dropping the concentration down to 0, the absorbance in a perfect world, or theoretically perfect world, would drop down to 0. But we also learn in spectroscopy that it isn't always 0, because maybe there's some background interference and different reasons for that. So you might leave the y-intercept term in there. And that's more another story for spectroscopy. But in general, you could cut out that y-intercept and say, oh, wait a second, the absorbance is directly related to concentration. What's interesting, though, is the slope actually has meaning in real things in science, and that's not always the case. Sometimes you get a constant that just relates things, but that constant may not be related to the nuts and bolts of the chemistry. This one is in particular. And here's what those things are. B is actually the path length. So getting back to that light passing through a cuvette, the path length of sample that the light has to travel through, literally in centimeters, is how we usually measure that. E is what's called the molar extinction coefficient, and we found out through multiple experiments that's actually dependent on the structure of the material. So here's this is a math introduction, not necessarily a thorough study of this spectroscopy, but here's what the take-home is, that basically the reason for log is that you can take a powered curve, graph it as the log, and it'll turn into a linear fit, and that's easy to do your math with. And in the case of chemistry, sometimes that slope, or even the y-intercept, actually has meaning in chemistry. And sometimes it's just a pure constant. And later I'll show you different tricks that we've learned to get rid of those constants if that's the case. All right, so one other thing I want you to learn about the log of a function is it's base 10. So here's a great little lesson that if you look at this, basically I'm starting with the decimal, not moved at all from the number 1. So when you take the minus log of t, I've moved the decimal place 0 times. So this is interesting that the trend works this way. Here I move the decimal point 1 time, so the minus log of t is 1. Now I've moved the decimal place twice, so the log of t is 2. Now I've moved the decimal 3 times, so the minus log of t is 3. And that's true of the natural log. It basically is related to factors of 10. So 1, 2, 3 does not mean that you're increasing by 1 each time. It actually means that you're increasing by a factor of 10. And here's another thing that you can pull out here, and this is related to spectroscopy, but it's something that we don't always understand, that when you look at this term that's called absorbance, which could be replaced, minus log t, that's absorbance. General in spectroscopy, people say, well, you should probably cut that off at 1.5 at the most, and usually useful information is somewhere between 0 and 1. And then the question becomes, well, gosh, why is that? Well, if you look in terms of the raw transmittance, this might help you understand that. That basically what you're doing is you get much past this, you're actually only working with less than 1% of the light. And so you're really approaching the limits of detection. Anywhere in this first range of logs, or absorbance range from 0 to 1, you're working anywhere from 100% of the light all the way down to, as I've shown you here, about 5% of the light. So that's 95% of the light that you're working with. So in terms of instrumentation, that means you have a very useful, strong signal. 95% of that signal is present. Then as you start to get to logs that are much higher than this, 2 and 3, Now you're using so little of the actual signal, okay, that it's actually becoming insignificant, and that's what we call LLD, or lower limits of detection of the instrument. So that's kind of a side lesson on spectroscopy, that really once you break too far above 1, you're getting out of the limits of detection for spectroscopy instruments. And that, once again, is a whole nother topic, and there's other ways you can learn how to quantify limits of detection. So in review, why introduce the log function? It allows exponential functions to be graphed in a linear fashion. That's what I just showed you. So that's important. With common log, numbers are power of 10. That was the other little trend I just showed you as well. So that's pretty straightforward. 2 applications in chemistry. Okay, just to show you where this is used. One is spectroscopy. I've already shown you that. These are not the only ones. I just want to show you a couple examples. The other one is pH. pH uses the same thing, where basically an increase of 10-fold in the concentration of H+ ions really represents a change of pH of 1. So how do you undo a log function? What's the anti-log? In other words, when we're doing math with this log function, sometimes we have to do the opposite to both sides. That's kind of the key to algebra, right? So I just want to get you on track here. Just like multiplication will undo division, 10 to the x, that is the anti-log of the log function. So let's just take a number. We start with 10. If we were divide it by 2, you could get 5. And if I took that number and I went the opposite and undid it, I would multiply by 2, and I get right back to 10. So multiplication is the opposite of division. Great. So let me show you how that works with log. Same thing. If I took the log of 1,000, I'd get 3. What if I had to undo that 3 and get it back to 1,000? Well, the anti-log of that, use it as the power to the base of 10. So let me just give you an example in algebra. All right, so let's say solve for y, and here's your problem. 4 times log of y equals 12. So here's what I've got to do. I've got to solve for y. I want to know what y is. So the first step in this problem is, okay, let's isolate log of y by itself. That's the first thing we're going to do. So now, to undo the multiplication between log y and 4, you do the opposite to both sides, which is divide by 4. So this really doesn't have anything to do with log math. This is just trying to isolate that log of y by itself. So now we've undone multiplication with division. Okay, so now we're ready, though, to undo the log. And just like we learned, okay, the opposite of the log is base 10 raised to that power. So if I use both sides as the powers for base 10, if that is the opposite of that, then basically y is going to fall out, equals 10 to the third. And we know 10 to the third is 10 times 10 times 10 is 1,000. And so here's the take home. If I had to undo the log, I'd do 10 to the x. If I had to undo 10 to the x, I'd use the log. Solve for y. If 6.02 times 10 to the y equals 0.019. And I just put this in here to remind you something. Later on in this talk, we're going to talk about the natural logarithm, and that it's a lowercase e. So this is something that's subtle, and it's come up with our application of computers, and that is when you do an uppercase E, and even on your calculator you'll see this, an uppercase E or an EE, that represents times 10 to the. It's a shortcut to get to scientific notation. Obviously somewhat related, but not exactly the same. So anyway, what I've done, now I've rewritten this. 6.02 e to the y means this. 6.02 times 10 raised to the y power. That's what that means. Equals 0.019. So now we're going to go through the same process. Let's do the algebra. First thing, let's isolate this powered function. So we got to get the 6.02 away from it. Do the opposite to both sides. Divide by 6.02. You simplify those terms. Now we got 10y equals this. The opposite, base 10 raised to some number, is taking the log. So you take the log of both sides. That y will fall out. And then if you do this on your calculator, enter 0.00316 and hit the log button, and you'll get negative 2.50. Here's a little application just to see how this works. If the pH of a solution is 5.5, what's the H+? What's the percent transmittance of if the absorbance of A is this? pH is minus log H+. So now let's solve this first problem. First thing then, is plug. Well, this is the pH, so we plug it in there. The first thing I would do is isolate the log H plus by itself. And that looks like it's isolated, but I actually have a negative sign, so I need to move the negative sign over. This is just one way to do it. As you know, algebra has many methods, and one isn't right over the other. It just might be what you're more comfortable with. So I'm just going to go one method here. So I got a negative 5.5 equals log H plus. Do the opposite to both sides. Opposite of log is base 10 raised to that power. H plus falls out. 10 raised to the power of negative 5.5, which is in essence 1 over 10 to the 5.5 power, ends up being a very small number. So anytime you see a negative exponent, you know it's small, less than 1, somewhere between 1 and 0. All right, so now let's do the same thing. You need a formula for this, and we just introduced this, but you might have seen it before. A equals minus log of t. So what's the percent T if the absorbance of A is 0.32? So same thing, plug, chug, move the negative sign over again. It's the analog, i.e. it's the power raised to base 10. You solve the transmittance as 0.479, but percent transmittance means let's express it as a percentage, which means move the decimal over twice, 47.9%. This is application of the common logarithm. Okay, so here's a practice problem for you to work on. I have given extra information just to remind you, just background information, but here's the formula you're going to work with here. Okay? But what is the A if the percent T is 65? Can you plug in solve and solve for A? So at this point, pause the video, work out your solution, and then when you get done, turn your video back on and you can check your answer. Okay, so let's see how you did. Convert to a decimal. This formula is based on T, not percent T. Plug and chug. And when you get done, you should get an A of 0.187. Here's another practice problem for you. If you're given this, what is the percent T? So now they're asking percent T. This will only solve for T. If the A is 0.05. So at this point, pause your video, work out your answer. When you get done, you can check your work, start the video again. So we get in here, we plug and chug. Remember to move the negative over. Take the analog on both sides. T is 0.891, but you're looking for percent T, so don't forget percent T means move the decimal over. So that was the common logarithm. So now you're going to see the natural logarithm, and look at your scientific calculator so you can see that there's two sets of keys here. So they're related, but they're not exactly the same. So let's start and look at this, the effect of changing temperature on a reaction rate, because I want to show you where this is literally applied. And the long story short is this. Many things that occur in nature, and also it occurs in finance as well, use the natural logarithm. And so, for example, as you raise the temperature, a chemical reaction will occur faster. And so what I've done is just showed you how many products are formed in molarity per second. And later on in this series, you'll be able to look at kinetics, and we go into this in detail. For right now, I just want you to understand, and I think with your background in General Chemistry 1, you can understand, as you raise the temperature, the rate goes faster. So once again, see that exponential curve? And we've learned from experience, oh yeah, you can graph that with a log, but in this case, this is a natural log relationship. It's an E relationship. So if you look at the rate constant, which really is directly related to rate, so as the rate constant doubles, the rate doubles, that sort of thing. So the rate constant is related to the temperature by the E function, but along with it, there's other parts. So once again, there's constants involved. And here's something we know about E. E is about 2.718. That's the base, just like base 10. Well, this is base 2.718. It does have a meaning in nature. The key to it is that things are growing continuously. In other words, with every change in temperature, not just this, for example, the graph, I've gone from this point to that point. But as you increase the temperature, even the smallest amount of temperature change, you're going to continue to increase the rate. So it's continuous. That's the key to this. And examples in chemistry are rate versus temperature, equilibrium K constant, which we'll talk about in general chemistry 2 versus temperature, the energy versus the equilibrium constant in a battery, and also nuclear decay rate. And I just would like to kind of send you off to a tutorial by Khalid Azid. It's online. He does an excellent job of helping you wrap your head around what base E means. So just like we talked about, the common logarithm log has its anti-logarithm 10 to the x. The natural logarithm ln has its anti-logarithm of e to the x. So here's an example of that. And this is from finance, and this is just a good example for us to practice on. So here's how this formula works. PT is your total earnings on some money. And this is the principal, or the amount of money you invest originally. So you invest some money, and it's going to compound with an interest rate continuously. So it doesn't just compound every week or doesn't compound every month. It compounds continuously. So this is that continuous exponential growth. So that's where E comes into play. And basically it says whatever money you invest times base E raised to the power of the rate of interest times the unit of time. So what we're looking for here in this question is, okay, we're going to put $125 in there. That's PO. And it's going to compound continuously for so many years. So that's the unit of time we're going to use is years. And what's the yearly interest rate we're going to apply? And so if I knew in 2 years, that's the T, I had $125, what interest rate would it take to make it grow from 125 to 145? And that's the final answer there. Okay, so here's how we solve this problem. We set it up, we plug and chug. So the first thing is we're going to try and isolate e to the r squared by itself, get that powered function isolated. So we're going to divide out the 125. So now we have e to the r squared equals 1.16. So now opposite to both sides. Well, what is the opposite of the exponential function e? And that is ln, the ln function. So we've got to take the ln to both sides. And r times 2 drops out. And if you do this on your calculator, take the natural log of 1.16, you end up with 0.148. And now you're left with just some simple algebra. I got to get rid of the 2, divide through by 2 on both sides. Then r equals this cut in half. And so now this is the interest rate. In 2 years, if you're gaining 0.074, but usually when you look at an interest rate, they report it as a percent. So let's move the decimal over twice. So at 7.4%, in 2 years, you could make $125 grow into $145. So here's a second point that I would like for you to take regarding the natural logarithm, and that is it's possible to convert between a natural logarithm and a common logarithm and vice versa. And the key is this formula right here. This is worth putting in your memory bank. Whatever your log of b is times 2.303, that will be converted into the natural log of b. So let's take an example. All right? So here's a formula from chemistry that basically says, look, if you want to know the voltage in a battery cell, you have all these constants. Some of them you're probably familiar with from general chemistry, like the universal gas law constant. There's the temperature. There's the number of electrons that are transferred, and this is Faraday's constant. But these are all constants times the log of, and here's that equilibrium K. So if I want to then use this exact same formula, but I want to use it in the form of the common log, all I have to do is implement the 2.303 times the log of K will be the same thing as log of K. That's how that would apply. Let's try and apply these now that I've shown you a couple examples. Okay, so now here's 2 problems that you can practice on. In the first one, I want you to re-express this expression that you'll see in acid-base chemistry when you get to that section in this class, which basically says that if you want to know what's called the POH, you'll learn more about that later, but this is just a plug and chug equation for you to practice on. The POH equals negative log of the OH concentration. Can you re-express this with the natural log function? And just to make sure you've done it correctly, use 1.03 times 10 to the minus 3 molarity and plug it into both of your new equations and make sure it turns out to be the same thing. Okay, in the second problem, I'm going to give you another equation that basically says the E cell equals 0.0129 times the log of K. Can you plug in the right numbers from this problem, which says, okay, at 298 K, so I don't need temperature, that doesn't plug in here. The voltage of a battery, which is marked as E cell, can be determined by the equilibrium constant, so that's what K is, the equilibrium constant, for a 2-electron reaction. So the 2 electrons taken out of here as well. None of that, that's just extra information. But the point is this: if you plug in 0.15 V for the E cell, can you solve for K? And once again, this is just to practice your algebra. So at this point, pause your video, work out your solution, and when you get done, check your answers. So let's see how you did. The first part, if you set up this equation, POH equals minus log of OH, and you convert it to the natural log, in this case you just divide through by 2.303. All right, now let's just see how we would check that. Okay, I'm going to take this concentration, I'm going to plug it in, and I'm actually going to do the calculation on my calculator. Minus log quantity 1.e to the minus 3 divided by 2.303, it ends up being 3. All right, now let's take the same quantity and plug it into the original equation. Although you should be able to look at that and remember how log works. If that's the power of 10, 3, then that should be the same thing. Minus log 1e to the minus 3, plug and chug, comes out 3, so this worked. Okay, in this case, we're just going to plug in 0.15 for the voltage, solve for K. So what are the steps? Got to isolate log of K by itself, divide through by 0.0129 on both sides. Cool. Now you have this expression. This is simplified. So how do you undo the log of K? The opposite, or the anti-natural log, is e to the x, right? So you do that to both sides. K falls out, and e to the 11.6 gives you a number of 1.09 e to the 5th. All right, so I hope this has helped introduce you to exponential functions, help you understand where they came from, how they're used in chemistry, and just some of the fundamental algebra moves to solve for an exponential function. And you'll find this to be very helpful in general chemistry too. So even if you have to run through this little video a few times or later on in the semester from time to time to remind you, it'll be worth it. So you'll be very comfortable working with exponential functions.